There we go. All right. So let me get this, minimize that. Okay. So now y'all can see my slide.
Yep.
All right, cool. Hi, my name is Mark, Mark Smith, also known as Smitty in some contexts. I don't care which one you use. Either one works well for me. I don't really have a preference one way or the other. On Twitter and on YouTube, I am Smitty Halibut, SmittyHalibut. There is a story behind Halibut that I will not be going into here just for lack of time. This was, whoops, not yet. This was a presentation that I gave at the QSO Today Ham Expo fall. Yeah, okay, the dates are right there, August of 2021. I also did two other presentations at the previous ones, one on audio building blocks for building audio circuits, and the other one was on, receiving, using GNU radio to, and cheap RTL SDR dongles to receive multiple different slices of RF spectrum and feed them off to different programs. So like in my case, I was receiving both the Whisper portion of the band and the FT8 portion of the band and sending them to their own individual copies of WSJTX to be decoded. You could also take the CW portion of the band and send it off to CW Skimmer, that kind of stuff. So with the GNU radio in the middle, you have all kinds of configuration options for doing all that kind of stuff. I guess I kind of already started doing this one. My call sign is N6MTS. Up until recently, I was known as KR6ZY, but I kind of trying to be better. I don't like the ableistness of being crazy. I used to think it was cool. I was wrong. And so instead I joined the initials as my call sign club. Once I noticed that N6MTS was available, I decided to switch over to it. As I mentioned on Twitter and YouTube, I am Smitty Halibut. And as Ed mentioned, I am the sometimes host of the Ham Radio Workbench podcast. Although that has become more official lately with the announcement that Jeremy has left the podcast. So Jeremy was replaced with four of us, me, Mike Walker, Vince Dion, and Rod Hardman. So Jeremy had to be replaced with four different people, and I'm one of those four. Okay, quick disclaimer about this presentation. I am going to be doing things very fast and loose. This is not a strictly scientific interpretation of this particular material. I'm going to be doing it in what I consider to be kind of a more engineering mode, where I'm going to be building a thing. Like I have a theory, I'm going to build a thing, I'm going to measure that thing, then I'm going to tweak it and test it and make changes to it and get to something that's good enough. At no point am I going to be analyzing the diameters and the mutual capacitances and doing all that kind of math hand wavy stuff. I'm going to be hand waving at all of that. So this is a very fast and loose take on this particular topic. If you want that more scientific, math-oriented, actual, like looking at the physics of how things works, I recommend these two articles. Ward Silver did one in Nuts and Bolts about 6 years ago. And then Chuck Kelselman has an article up on his website on common mode chokes. And I've actually, since doing these slides, I found a third article that I will try and find the link to and send to you guys, to y'all. But there are much more scientific approaches to this topic than what I'm going to be doing today. So what is it that I'm bringing? There are two things. One is that I'm going to be bringing measurement. I actually want to build a balun or a one-to-one balun or a common mode current choke. And we'll talk about what that means in a bit. I want to build a thing, and then I'm going to measure that thing and see how good of a job this thing is doing at what it is that I want it to do. And to be able to do that, I needed to build a test rig. And so I'm going to be showing the design of that test rig. So those are the main things that I'm bringing to the table here is the test rig. How do you actually measure this thing? And then showing the measurements of the things that I built. At no point do I claim that this is comprehensive. There are all kinds of balun designs that I will not be talking about today that may be your favorite balun design. And if I don't cover your particular preferred balun design, by all means, take what I'm doing here, build your own test rig, build a balun, measure it, and then post the results. This is not comprehensive. I did not have, infinite amount of time. So I went through and built a few different common mode choke designs with the materials that I had on hand and was able to measure that. And that was enough to kind of demonstrate the concept. So I'd love to see a different balun design if you've got anything. All right, so what is common mode current? And what is it, and why are we trying to get rid of it? So so let's look at what common mode is first. If you have a transmission line, and in this drawing, we're looking at like just a 2-wire transmission line. This could be twin lead. This could be coax. This could be your power cable. This could be a USB cable. This could be an Ethernet cable. Anything where you've got 2 wires and you want to send power down those 2 wires. That is a transmission line. So if you look at those 2 wires and the current on one wire going this direction is, if that current is exactly balanced by the same amount of current going the other direction on the other wire, right? So you've got current going this way and the same amount of current going that way. That is called differential mode current, okay? Because they're going in different directions. In an ideal transmission line, all of your current will be differential mode. You've got current going this way, there's a voltage across your load, the current going through that load delivers power, and then the return current comes back the other way. But sometimes you have an imbalance between those 2 currents, right? And so let's say I've got 3 amps on the top wire going that direction and 2 amps on this wire going this direction. Well, I've got 2 amps of differential mode because I got 2 amps this way and 2 amps going that way, but I have an additional amp going this way. So that's 2 amps of differential mode current and 1 amp of common mode current. All right. Now, those common mode currents cause problems. You want the currents in your 2 different wires to be perfectly balanced. Anytime you have an imbalance in those currents, that causes problems. Notably, because Kirchhoff's current law tells us that that current has to go somewhere. You can't have magically have current going down a wire and then just have it evaporate. Like, it has to go somewhere. And where that goes is typically not where you want your power going. And the diagram that I've shown here, the example I'm using is that it goes to ground. And that causes all kinds of problems. So the transmission lines that I showed in the other one was just 2 wires. Coax has kind of a special property about it. I am not going to go into the physics of why this is, because it was explained to me at one point and I understood it at the time. I would not be able to explain to you why it is now. So I'm going to hand wave and ask that you trust me on this. Physics says that if you've got current going down the center conductor of a coax, that there will necessarily be the exact same balanced current coming the other direction on the inside of that shield. Necessarily, okay? So that means that if you've got a perfectly balanced, perfectly differential current, you got current going this way on the center conductor, and you have a perfectly matched amount of current traveling the other way down the shield, all of that current will travel on the inside of the coax. But if there's any imbalance in the currents between the center conductor and the shield, you will still have a balanced amount of current on the inside of that shield, but the difference will travel on the outside of that shield. So let's go back to the earlier example. I've got 2 amps of current going down this center conductor. This is a contrived example because of where the currents are. Trust me on this one. I got 2 amps of current going down the center conductor, and there's attempting to be 3 amps of current coming back. You're never going to have 3 amps of current coming back from your antenna, but hand wave at the example for a second. So what that means is you're going to have 2 amps on the center conductor and 2 amps on the inside of that shield. And then the 3rd amp is going to come down on the outside of that shield, right? So the amount of current on the inside of your coax is necessarily always balanced, which a weird special case of that is, let's say you're just using the center conductor of your coax as a wire. You don't have anything attached to the shield at all, and you're just using it as a wire, and you're passing a current down that center conductor. Well, if you've got an amp of current going down that center conductor, you necessarily have an amp of current going this way on the inside of the shield, but that current needs somewhere to go. So it goes to the end of that shield and comes back on the outside. And so I've got 1 amp of current going down the center, 1 amp of current coming down the inside, and an amp of current going on the outside, which basically means any common mode current on the center wire of your coax will necessarily travel on the outside of the shield. It's kind of a weird special case, but that's the way it works because fields go and things happen and all kinds of things. All right, let's move on. So what causes common mode current? Where does common mode current come from in a typical antenna system? There are all kinds of things that can do it. We're going to be concentrating on 2 different things that are common sources of common mode current. The first one is an imbalanced antenna, right? So if you've got coax going up to a dipole or twin lead going up to a dipole, it doesn't matter, and one of those wires is a little bit longer than the other, or one of the wires droops down a little bit more than the other, or it's closer to the metal of your gutters on your house, or any of 1,000 environmental reasons that antenna is not just a perfectly symmetric wire in empty space, right? There is no such thing as a perfectly symmetric wire in empty space. Every antenna is going to have at least some amount of imbalance in it. So when you have an imbalanced antenna like that, where it's not exactly the same on both sides of that antenna, that's going to cause a little bit of common mode current to be reflected back down the coax of your feed line. If your antenna is pretty good, then it's going to be very little current, and it's generally not anything that we worry about. But as your antennas get more imbalanced or more non-perfect environments, you're going to have more common mode currents down, and you'll want something at that feed point to stop that common mode current, and it kind of forces all of that imbalance to be resolved up at the antenna, and you want all of that current radiating out the antenna. We'll look at what that looks like in a second. The second source of common mode current is, oops, no, don't show the next slide. Remember how I said that a coax connector is actually, or a coax cable is actually 3 conductors. You got the 2 in the center that are necessarily balanced, and then you've got the outside of the coax, or like you've got the center wire and then the inside of the shield. God, I keep using the wrong words. The center conductor and the inside of the shield are necessarily balanced, and therefore necessarily differential mode current. And then you've got the outside of the shield, which is where all the common mode current goes, right? So these are a transmission line, and this is just a wire going from your transceiver out in the world. However long your coax is, that's how long this wire is. Well, guess what a wire is? That's an antenna, right? And so your coax, the outside of the shield of your coax, is an antenna, and it's going to be receiving a whole bunch of noise. So the outside of your coax is receiving whatever energy is nearby. So if you've got any switching power supplies that are radiating a bunch of noise, or the washing machines get a lot of hate these days, LED lighting, whatever it is that's creating electrical noise, or lightning strikes or anything like that, right? All of that's going to come in on that big long coax that you have that is electrical noise. And the problem is, like, if your transceiver and your ground were perfect and 0 ohms impedance, then all of that current would just come in, go through 0 ohms in your transceiver into your ground, and it would dissipate and it would not be a problem. But there's no such thing as 0 ohms. There's always going to be some impedance. You know, it may be 1 ohm or a very capacitive impedance or a very inductive impedance, whatever it is, there's going to be some impedance between that coax and ground. And when you have that impedance, that current flowing through that impedance is going to make a voltage. Ohm's law. You got current, it's going through an impedance, that's going to produce a voltage. And that voltage in your ground that's supposed to be pure 0, you've got now a voltage where there's not supposed to be any voltage, and that's going to show up in your receiver as noise. So when we talk about common mode chokes being good at eliminating receive noise, that's the mechanism that received noise comes in. So what does this mean? Where do we want to put these chokes to address both of these issues? And that's what this next slide is for. So there are actually 2 places that we want to be able to put common mode chokes. The first one, to solve the first problem with the imbalanced antenna, is to put a choke up at the antenna. So all the transmission line, you've got your differential mode currents going up through that transmission line. It passes right through the common mode choke, and I'll show you how that happens in a little bit. But all of that differential current passes right through the common mode choke, goes up into your antenna. Your antenna is a little bit imbalanced, but there's no way for that imbalanced current to come back down the outside of the wire, because the choke is a high impedance. The choke is a higher impedance to common mode current than the antenna is. And so in the voltage divider that forms, all of the power is dissipated by your antenna. So this is why it is common practice to put a 1-to-1 balun or a common mode current choke at the feed point of your dipole antenna. If your dipole antenna were perfect, you wouldn't need this. But there's no such thing as a perfect dipole antenna. They're always just a little bit off. And sometimes they're a lot of bit off. And a common mode current choke or a 1-to-1 balun at the feed point of your antenna can fix a lot of those problems. The second place we want to put a common mode choke is right at the transceiver. So we want to disconnect that third wire. We want to make a high impedance to that current that this wire is finding, right? We don't want that current to come through this transceiver. You got a high impedance here and a low impedance here in your transceiver, then very little of the voltage is going to form over the transceiver. Most of the voltage is going to form over that choke. And that's what we want. So we want to basically disconnect the third wire of your coax from your transceiver, and we want to force the currents in your antenna to be balanced. So that's what a common mode current choke does. Let's look at how it does it. Okay, so basically what we want a common mode current choke to be is a device that we can stick in our transmission line that is transparent to differential mode currents, right? So we want differential mode right through this thing because the differential mode of current is what we want. But we want it to be a very high impedance to common mode currents, right? So a near 0 ohm impedance to differential mode and a near infinite impedance to common mode current. So how do we do that? Well, there are lots of different ways of constructing a common mode choke, but they all basically boil down to this mechanism. When you've got a current passing through a wire, it makes a magnetic field around that wire, right? And if you take that wire and you wrap it up into a coil, that makes an inductor, right? So the magnetic field in this inductor, because of the way you've coiled this wire together, all those magnetic fields of that wire reinforce each other. And the effect of that magnetic field actually goes up as the square of the number of turns, which is pretty cool. But that magnetic field has an inductive effect. And an inductive effect in this particular case just means that it is a high impedance to low frequencies. No, the other way around. It's a high impedance to high frequencies and a low impedance to low frequencies. But as long as we make that cutoff point between high frequency and low frequency in the lower than the range that we're trying to operate, like we want it to be a low frequency cutoff so that all of the RF spectrum is high impedance according to that inductor. That's what we're looking to do here. So if you've got current going this way, it sets up, let's see here, right-hand rule. If I've got current going that way, the magnetic field is wrapping around the wire this way, right? But if I've got current in another wire going that direction, right-hand rule, it's going, the magnetic field is going the opposite direction. So current going this way creates one magnetic field. Current going that way creates the opposite magnetic field. Those two magnetic fields cancel each other out. And when the magnetic fields cancel each other out, there's no magnetic field for the inductor to do anything with. So basically, that inductor becomes completely transparent to those differential mode currents. So if you've got two wires that you wrap up into an inductor with each other, anytime you have balanced currents, those balanced currents will flow right through that inductor because the magnetic fields have completely canceled and there is no magnetic field for that inductor to work on. But if you have any imbalance, any common mode current, that common mode current doesn't have a magnetic field to balance it out, and so it does act as an inductor. So that is how this I keep pointing it to my screen up there. So that is how a common mode current choke works. The differential currents cancel out their magnetic fields, and it is not seen by the inductor. But the common mode current doesn't have anything to cancel it out, so it is seen by the inductor. And if you make that inductor a large enough value, then the frequency will be low enough and it will look like a high impedance to the frequencies that you're trying to operate at. Okay, moving on. So we are going to use a nano VNA, everybody's favorite cheap tool, to measure these common mode current chokes. I am not going to talk about how to use a nano VNA. That is not what this talk is about. This talk is about the balance. There are a lot of other really good presentations about how to use a nano VNA and how to calibrate it and all that kind of fun stuff. But I am going to talk at least enough about the nano VNA to know how we are going to be using it. So VNAs in general, also the nano VNA, are typically have two ports. And what it does is it generates a signal on one of those ports of a known amplitude and phase. And then it is able to measure that signal on both of the other ports. And it measures the relative amplitude and the relative phase to the signal that it generated. So that's all that that's all that a VNA does. So it generates a signal here, and it knows what the amplitude is and it knows what the phase is. And then some of that signal is going to bounce back and it's going to come in through the same port that it was sent out, right? Just like a reflection on a poorly matched antenna, right? So that reflected power, it's going to measure the relative amplitude and the relative phase of that reflected power. And when it is measuring the reflected energy, that is called an S11 parameter. What that means is it is a signal that was generated on port 1 and is being measured on port 1, okay? That's where the S11 comes from. S21 means that the signal was generated up here on port 1 and it is measuring through the load and it's measuring the result on port 2. It's measuring the same thing, but on a separate port. And those are called S21 parameters. We generated a signal on port 1 and we are measuring it on port 2. These are not S11 and S21. And it makes my teeth itch whenever people call them S11 and S21. I don't know why. It's S11 and S21. When you are calibrating your VNA, when you do the open and short and load calibrations, you're calibrating port 1. And when you do the isolation and through calibrations, you're calibrating port 2. Okay. So we're going to build a test rig. How do we measure the effectiveness of a ballon? I'm going to be using coax because those are all the ballons that I make. I don't do anything with twin lead, but everything that we're talking about here applies to any transmission line. In fact, I lied. I do have a common mode current choke on various network cables, like the Ethernet cable into the back of my Flex. Anytime I transmitted over about 20 watts, it would cause my Wi-Fi to drop out. So I ended up putting a common mode current choke on that Ethernet cable, and that problem is gone. Those kinds of things. Right? Like these are the kinds of tricks that you can do with common mode current chokes once you understand what they do and how they work and how to make one effectively. So, but for RF perspective, I'm going to be using coax. So let's take a look at our favorite 3-wire model of a piece of coax again. We have the center conductor and we have the inside of the shield. That's where all the differential mode current goes. But we got to find a way to get current on the outside of that coax, right? The nano VNA normally sends the signal on the center conductor of the coax and is pulling a balanced amount of current coming back on the shield of that coax. So all of the current is differential mode and it stays on the inside of that coax. The outside of that coax doesn't really get tested in any way. That's kind of the glory of coax, is that you can move it around and bend it and do whatever you want. And all the signals stay on the inside. So what we need to do is we need to find a way to get the signal that the nano VNA is measuring on the outside of that shield. And the way I do that is with this very simple circuit, right? So on the left-hand side here, we've got the ports that connect to the nano VNA. This is just a standard SMA port. And I'm going to take the signal from the center conductor of the SMA coming from the nano VNA, and I'm going to wire it to the shield of a connector on the other side for my ballon to connect to. And then on the return side, I'm going to do the exact same thing. Take the shield from the device under test, the ballon that I'm trying to measure, and connect it back to the center conductor of the port over to the nano VNA. Now, because of return currents, we do need to connect the shields from the nano VNA here together so that the return current has a place to go. But we're basically taking a coax, kind of peeling it open, taking the center conductor out of that coax and putting a ballon on that center conductor, right? And so this is the first test rig that I built, just a cheap plastic project box. These are the SMA ports going to the nano VNA. And you can kind of see, you can see it better on this one, that the shield of that SMA port connects straight across to the shield of the SMA on the other side. And so that's the ground connection. That's this wire right here. And it just connects straight across, so the nano VNA has that wire, has the return path. But the center conductor of my connection from the nano VNA goes off to the shield of the SO239 up here. The center conductor of the SO239 isn't connected to anything. I'm connecting it to the shield here. And then from there, I want to be able to test cables with different types of connectors on them. So I have the SO239 and a BNC and an SMA. And they're all just connected in parallel. It just allows me to use whichever one of them I want. But again, you'll note that it's connecting to the shield of that BNC and that SMA. The center pins are not connected to anything. And then I just got the return path on the other side, right? Well, this worked well, but it made calibration difficult because there was no way for me to hook up my open short load calibration slugs to this system. So I had to take this out of the system to be able to calibrate it. And that's kind of not how you want to calibrate things. Excuse me. You want to calibrate your VNA with as much of your test rig as possible, because what it's doing is it's measuring the effect that your test rig has on that signal, and it's compensating it for it. And so you want as much of that in there, because otherwise you're going to be measuring the effect of not just your ballon, but also of your test rig. So you want, ideally, what we would have is we would have something that would allow me to hook up those slugs, those test slugs, to this test rig for calibration, and then still be able to connect up the ballon for measurements. So I built a second version of it. Here, the center conductor connects to the center conductor of the test port, but I also have a switch that will either connect that center conductor to the shield, thereby putting the signal on the shield, or that shield can be connected to the shield on the nano VNA. And so when the switch is in the 1-2 position, that's in the test position. So it is, you can measure the balun in that position. But when you have it in the 3-2 position, that is called through. And it just looks like a coax cable with a little bit of a bump in there because it's got a connector and it's not perfect coax, but it's still relatively small. And that makes it a lot easier to hook up my test slugs over here to actually calibrate with the test rig in place. And then of course we did the same thing on the other side. So what does this one look like? This is the second test rig that I built. You also notice that I added N connector here. So again, I've got the 4 different connector types just because I've got lots of different cables with lots of different connector types. And I've got them in 2 groups, right? The port 1 side and the port 2 side. And then inside the box, all 4 of those cables go down to that switch, which is implementing this here. And then the output of that switch just goes to an SMA on the backside that we use to connect up to the nano VNA. All of these connectors were just 1-foot patch cables that I bought on eBay. So I bought 2 N to SMA, 2 SO239 to SMA, 2 BNC to SMA connector or 1-foot patch cables, and then cut them in half. And when you do that, you end up with 2 Ns, 2 BNCs, and 2 SO239s. And then the other side of them was all the SMA connectors. And so you got plenty of SMAs, panel mount SMA connectors. And just then I didn't have to crimp any coax cables, and it was only a few bucks. You can get them on eBay super cheap and easy. And it made the assembly of this so much easier. Here's a close-up of the switch, of how I did the switch. So you'll notice the center conductor just goes straight on through. And then on the device under test ports, the shield can either connect to the center conductor or to the shield of the SMA port or the nano VNA port. Okay, moving on. So when you're calibrating your nano VNA, normally calibration is always important with a VNA. And this is a thing, this is a fact that I think most people who use VNAs don't fully appreciate. Always, always, always recalibrate your VNA, whether it's a nano or not. Recalibrate your VNA anytime you make any change to your setup. That includes switching out a cable. That includes putting in an adapter. That includes turning it off and back on again. Anytime you make any change to your setup, recalibrate it. Just trust me on this, and make sure you're calibrating it over. Will you stop it? Make sure you're calibrating it over the full range of frequency that you're going to be running your tests at. If you calibrate it for just the 20-meter band and then measure over the entire HF spectrum, that's not going to work out so well. Ask me how I know. All right, so when you're calibrating your nano VNA, the open, short, and load calibrations, you test it with the test rig in the through state. You flip the switch over to the through, and then when you're testing isolation and through, ironically, you put the test rig into the test state. And that is how you want to calibrate this particular test rig. All right, once you've got your VNA tested, I strongly encourage you to validate your calibration by taking 2 very simple measurements. First off, these graphs are generated with a software package called Nano VNA Saver. It's a free package. You can download it. It runs on Mac, Windows, Linux. It connects to the Nano VNA over USB and it really improves its capabilities. You can go over a much wider frequency range with much higher precision, because normally the Nano VNA only measures 101 data points. And so if you tell it to measure between 3 megahertz and 30 megahertz, you've only got 101 data points across that entire 27 megahertz range. And that's not very precise. But Nano VNA Saver, you can say, yeah, do that in 27 different chunks, and then you're measuring 101 data points every megahertz, right? And so what is that? Every 10 kilohertz worth of precision. So you get much better graphs out of it. A lot of things you can do with Nano VNA Saver, highly recommended. That's where all these graphs came from. So we're going to be seeing lots of those graphs. So test or validate your calibration by measuring it. What is it we're measuring? We're measuring the S21 gain. And we'll talk a little bit more about what we're measuring in a second here. But the S21 gain. And so a big negative number means that there is very little signal coming back. It's generated a signal and very little of it is coming back, right? So when there's no cable connecting the input to the output, you want the S21 gain to be a very large negative number. 90 dB, I think, is about somewhere between 90 and 80 dB is about the limit of the Nano VNA. It just doesn't have very good dynamic range. It is $50 piece of hardware after all. Now you'll notice that my rig is not great. It gets up to 50 dB, so around the top end. I think that's because the test rig, there's no shielding here. Like all of these are capacitively coupling to each other, and as you get higher in frequency, these become a larger percentage of the wavelength, and so they're gonna look like much more of a wrinkle in the wire as you get higher in frequency. If you really wanted to do this right, you would build this in a metal box, but you can't connect the shield of these output connectors to that metal box because that would short them out, right? So you need isolated connectors because we're putting a signal on that shield. So if that shield is connected to the grounded metal box, you just grounded your signal. So you can't do that. That's why I used a plastic box, but that does mean that we're going to get a lot of bleed over in the higher frequencies. But test your calibration with a totally open, and you should have something that is a whole lot of loss. Ideally it would be around 70 to 90 dB. Mine kind of got not so great up here at the top. And then you want to test with a jumper cable between those two ports, just a cable going from one to the other. And that should be very little loss, right? Again, down here at 3 megahertz, we've got basically 0 dB of loss. And up at 10 megahertz, we've got not even a dB, right? So because this is from a 0 to 10 range, so less than a dB worth of loss on the high end, right? So this is pretty good. This could be better, but here we are. Point being, validate your calibration, and because I've seen some where my calibration was off and these graphs were way worse. All right, so I just talked about what we're going to be measuring for in a bit. What does good look like, or good enough look like? What is it that we are looking for to say that this balun or this common mode current choke is doing its job well? Well, we're going to be measuring the S21 gain, and we're looking for larger negative numbers, right? So we want less gain. A larger negative number is better. Well, how much? Well, I mentioned earlier Chuck Kauselman. In that article, he's talking about at least 1,000 ohms. And if you're measuring 1,000 ohms in series with a 50 ohm load and lots of math, I promised you there wouldn't be any math in this presentation. So you can go back and take a look at that slide if you want. I'm going to wave my hands and say 25 dB of loss or better. 1,000 ohms turns out to about minus 25 dB of gain or 25 dB of loss, which are different ways of saying the same thing. And unfortunately, I think I go back and forth. So minus 25 dB or better being a larger negative number. But that's not the whole picture. So I'm going to give you a sneak peek of one particular balun that I measured here, which I call a ugly Gordian knot. And we'll look at this slide again, or this picture and this graph again later. The point being that look at this graph. Man, that is minus 40 dB. That is a fantastic balun. And if you just measured its peak point, you'd look at that and say, that's way better than minus 25 dB. That's fantastic. Except that its minus 25 dB bandwidth is about from 20 to 25 megahertz. So if you were trying to go to, what is that, 12 meters, that would work great. But outside of that, it's not fantastic, right? So we need to update our definition of what good enough is. not only are we looking for 25 dB of loss or better, we're looking for it as across as much of the HF spectrum as possible, right? So that's what we're looking for. 25 dB of loss across as much of the HF spectrum as possible. All right. I have teased this enough. I'm not going to hold out on you any longer. I'm just going straight to the results. What was the best common mode current choke or one-to-one balun that I measured? And the best one that I could measure was about 13 turns of coax around a toroid. Now, if you're going to be one of the people who has, a lot of people have strong opinions on the type of mix on a toroid. I don't. There are two numbers that the toroids are ferrites in general are made up of a clay, kind of a ceramic that's a mix of iron and some other metals and things. And exactly the recipe that goes into that mix gives that material different properties. And there are two main types of mixes that do really well at HF. One of them is called 31 mix, and the other one is 43 mix. There are people who have very strong opinions and will get into very heated debates about which one is better. Let me give you a spoiler. They both work great across the entire HF band. If you are optimizing a balun for the lower half of the HF band, use a 31 mix. It'll work a little bit better. If you're optimizing a balun for the upper half of the HF band, let's say you've got a 20-15-10 meter tri-band antenna, but you don't have 40 or 80 or anything else, use a 43 mix. It'll work a little bit better. If you're building a high-end, a high-band antenna, 20, 15, and 10 meters, and all you've got is a 31 mix, use it. It'll work. It'll be fine. You may have 1 or 2 dB less rejection than if you used a 43 mix, but it's still going to be better than not having a balun on there at all, right? We are amateurs. We are engineers. We slap stuff together and see how it does. It'll be fine. So I'm not going to get into the 41 versus 33 mix debate here, other than what I've already done. But use a toroid and wrap your coax around it as much as you can. This graph right here is from this balun, okay? So this is 13 turns of RG316 around an FT 140-43. So the FT means it's a ferrite toroid. 140 means that it is 1.4 inches. So 140 is the number of hundredths of an inch of outer diameter of that toroid, the outer diameter. So it's the size of the toroid. So FT 140 is a 1.4 inch outer diameter toroid, dash 43, which means it's a 43 mix toroid. Remember, I talked to you about 43 versus 31. They're both going to work fine. And look at the results of this. It is better than 25 dB. It's better than 30 dB across pretty much the entire spectrum, and better than 35 across a whole lot of the spectrum, right? So this is a really good rejection of common mode current and across the entire spectrum. Far and away, this is the best balun that I've measured during this test. Here's another one that I made of RG8X across an FT240. So a larger toroid. It needed a larger toroid because of the larger cable, 2.4 inch outer diameter, 43 mix. And the performance of this one, I don't have the graph up here, but it was pretty dang close. I think it was a few dB less because it actually had one less turn. That was as much as I could fit through the center without scraping the inside of the toroid. So I think this is a 12 turn, and it's like just a few dB less rejection. But these are far and away the best toroids, but are best common mode current chokes I have found. But they're not the only good ones. We do have some other ones that we're going to go look at in a bit. All right. Okay, well, I guess we're going to go with the second best option as well. The second best option, if you've got coax that already has connectors on it, but you've got some slack in it, you can't feed it through a toroid very easily with those connectors on it. So instead, wrap it up in, I call this a 3-turn, even though there's only 2 of them up here. It's because you measure inductors by the number of times the wire passes through the ferrous material, right? So if you've got a toroid, how many times does that cable pass through the center of that donut? Well, these clamp-ons up here are basically very large toroids. And so if it passes through once, comes around a second time, comes around a third time, it passes through that ferrous material 3 times, there's only 2 loops on the outside, but that's still a 3-turn coil, right? So that's what I mean when I say a 3-turn coil. You're going to make 2 of these, or even better, 3 of them, in series on your coax with 3 turns in each of these coils. Don't do more than 3 turns. And we'll talk about that one in a second. We'll get to that one in a second. So you want to build 2 in series, 3 turns each, with a clamp-on ferrite around that. The big advantage to this is that you can do this in cable that's already in place. You can kind of coil up the cable, put the clamp-ons on it, and as long as you've got enough slack, you can stick a common mode current choke on your cable. Let's look at the response curve of this one. It's better than 25 dB all the way across. It's not as good as the toroids. It's about 5 dB worse than the toroid, but it's still better than 25, and it's all the way across the HF spectrum. So this is a very good balance. If you were to put a third one of these in series, it would basically match the toroid that we looked at earlier. Okay, so I showed you this one earlier. Gordian knots. So there's a common theory with coax that you can just take a coax and make an inductor out of it, wrap it around a bunch of times. And ideally, you would do that on a form, like a piece of PVC pipe or something like that, and wrap that around in an actual coil. But in a pinch, you can just wrap it around itself and kind of tie it up in a knot like this. Don't do that, at least not with more than 3 turns. And the reason for this is, look at this spiky graph. So what's going on here? We're gonna see this in more detail a little bit later. Not only have you added a whole bunch of turns, dang it, not only have you added a whole bunch of turns to the inductor, but you've also added a whole lot of mutual capacitance. There's capacitance from one turn to the next, and all of the cables can talk to all of the other cables and have capacitance to all of the other cables. And so you've got a whole lot of mutual capacitance in this coil. And when you've got a capacitor in parallel with an inductor, that forms a resonant circuit. And this particular resonant circuit happens to resonate at about 22 megahertz, right? It is great at blocking energy at 22 megahertz. But unfortunately, the inductor and the capacitor work together to make it not so good outside of that frequency range. Oh, this blue line here, you're going to see this blue line on all graphs going forward. This blue line is it's our reference. That is the line from the 13 turns of coax around a toroid. That we're comparing all of these other balance to that one, because that was the best one that I measured. And so we're going to see how all the other ones measure against that one, just as a kind of a point of reference. So you don't want to just wrap your coax around and around and around and use it that way, because it won't work very well. If you wrap it out cleanly across a form, it does have less capacitance and it does resonate a lot less, but there are it still has some capacitance, and there are ways of doing it better. If that's all you've got, go ahead and do it, but definitely don't coil it up like this with a whole bunch of coils.
Smitty, Mark, can I interject with a couple of quick questions?
Yes.
On your reference balun, did you try doing more than 13 turns at all? And what was the result? Was it diminishing returns? Is that, in other words, if you'd had 15 turns on the toroid?
No, I just ran out of cable. No, I did not try different numbers of turns around the toroid.
Okay.
I looked online, and a lot of people say 13 turns. And so that's what I put around that cable. I don't think you would get diminishing returns. If anything, it would continue to improve because the inductance goes up with the square of the number of turns.
Okay, and then the other question is when you talked about the capacitance of the ugly balun, does the toroid prevent the capacitance or block the capacitance, and is that why you use the toroid, or do you know?
No. So the toroid, I mean, I guess technically no, because it's still very similar to like wrapping it around a circular form. What's going on here, and the reason that this works so much better, is because I never actually talked about what ferrite material does. Ferrite material is like a very high conductivity for magnetic fields, right? Your magnetic field is out in the open space and it can go through air, but the air is kind of a lossy material for a magnetic field to go through. So by putting this magnetic field in the space where this ferrous material is, it's a very low impedance, a very high conductivity for that magnetic field, what basically means that the inductance you get out of the same physical form of a coil of wire is much higher.
Higher
It
pervious.
greatly improves the efficiency of your inductor. And so if you were to take this ferrous material out of here and just replace it with air or something that, you have the same coil of wire, but make the ferrous material dissipate or disappear, you would still have a balun there, but the inductance would be much lower. And the balance between the inductance and capacitance would be closer to a resonant circuit.
Gotcha. Thank you.
Yeah. So it's more about the ferrite than it is about the toroid. The wrapping wire around a toroid just happens to be a very efficient use of ferrous material. And it has other properties as well, but it's a very efficient use of ferrous material. You get a very efficient inductor, and it's much more to much closer to a perfect inductor without any resonance. Or it has resonance, but it's at a much higher frequency. And kind of the same thing here, right? Like, so if we're actually going to see it in a bit, I measure these two knots without the ferrite clip-ons, and then I measure it with the ferrite clip-ons, and you can see the effect that ferrite clip-on has in the response curve. Okay. All right, so let's look at these Gordian knots. So this is a Gordian knot with 2 turns. And again, remember that the turns, is the number of times that the coax passes through that area there. So it's actually 1 coax in that loop around the outside, right? So this is kind of the smallest number of turns that you can do. So with 2 turns of a Gordian knot without any ferrite on it at all, just a loop of coax, you get some rejection, not a lot, about 5 dB kind of average. At the best, it gets down to 10 dB up at the high end, but it's kind of a far cry from our reference. 3 turns, it still doesn't look quite as good as 2 turns, but it's better. It it goes down lower a little bit faster. It stays down around 10 dB longer. It's better, but it's still not great, but it's got a pretty good shape. It's relatively flat all the way across the band. Now, if we go up to 4 turns, it's a lot better. It's a lot more loss up here, but you can see that it's starting to kind of downslope. I'll bet you the resonant frequency is right out here, somewhere around 50 megahertz, right? You're starting to see that resonance come in from that mutual capacitance. Then you get to 5 turns, and you've got that resonant peak inside the HF band. I think the ugly balun over here was actually 6 turns. So this was a 6-turn balun, and here I'm just showing the graphs up to 5. So there's a 5-turn balun with no ferrite material on it at all. And you see that resonant inside the band. So the shape is kind of really crummy here, and it's kind of starting to show crumminess here. But the shape on these two isn't that bad. Their loss isn't very good. All right. So what happens when we add ferrites to these Gordian knots? Well, here's the same graph that we had on the previous page. There's the graph for 2 turns with no ferrite material. But let's add a clamp on. Let's add 1 ferrite clamp to this coil. It doesn't show here because I couldn't figure out how to get Nano VNA Saver to fix the scale. But this is -10 at the top of this graph, and this one is -0 at the top of this graph. So in the best case, with no ferrite, we're -9 dB in the best case, and over most of it, we're around -5 or 6 dB. All you have to do is add a ferrite clamp on to that balun, and you're down around -15 to -20 over most of the band. So adding that ferrite material, just that 1 clamp on to those 3 turns, greatly improves the performance of this common mode current choke, right? It is a lot closer to this than this one is. So what happens if we do the same thing with the 3-turn balun, right? Here's the same graph that we saw on the earlier slide for 3 turns, but then we add 1 ferrite to it. And again, we're down, it's improved by about 20 dB. We start out at 20, we max out at about 25. And then by the time we get to the top of the HF band, we're back up around 15. So you can kind of see some of that resonance coming in here. But it's still relatively flat. We don't have a super deep and sharp resonant point. And the reason we don't have that super deep or sharp resonant point is because we only put 3 turns in that ugly balun. As soon as you go to 4, you start seeing those spikes. That's why I said at the very beginning, do not put more than 3 turns in your coils. All right, so at 4 turns, here is that ugly spike that I was just talking about, right? So we have that resonant point. Over here, this resonant point was up around 50 meg. By putting that ferrite on, it brings that resonant point down. It also improves the loss characteristic, but it's moved that resonant point down into the HF spectrum. And then 5 turns, again, you know, here it is without the ferrite, and here it is with the ferrite. Of all of these, 3 turns had the best shape. We just needed to have more loss. So what does that look like? Well, if 1 of those on your coax was good, putting 2 of them in series ought to be better, right? And sure enough, this went from starting at about 20 and peaking out at about 25 to starting out at 25 and peaking out at about 32. So we've dropped it another 5 to 10-ish, 5 to 8-ish dB, but it's also improved the high end a lot. It's flattened it out. This is a much flatter curve than this one is. This curve kind of spans about 10 dB. This one kind of only spans about 5. Ignore that up there. So it's flattened out the curve. Why is that? Why does adding a second balun, a second common mode current choke in series flatten out the curve? There's a very good reason for that. Inductors in series add their inductance, right? Okay, great. So now putting 2 of them in series means that we have twice as much inductance in series. But putting capacitance in series divides the capacitance. So by building 2 relatively low loss baluns and connecting them in series, we are adding their inductance and dividing their capacitance. And so the result of these 2 baluns in series is better than just twice of one of the baluns, right? So that's where you're actually seeing this curve flatten out, because we're getting less capacitance and less of a resonant point in this. It's being dominated by the inductance much more. It's much less resonant. And if you were to add a 3rd one, I just didn't have enough coax. I would have tested adding a 3rd one, but the coax that I was using for all of my tests was just too short. If you add a 3rd one in series to this, that'll probably line up pretty darn close to our reference graph. So that's kind of the result that I came to as the second best option. If you can't use a toroid, then do this. And I've actually gone out to my antennas out on under the house and done that. I had some slack and some coax, and I just folded up the coax and put some clamp-ons on it. I've got an RF patch panel up here that I use usually about 2 or 3 foot coax cables to connect inputs and outputs. And I've swapped some of those out for 6 foot coax cables that I've put clamp-ons on, or actually I've got some ferrite beads that are like tubes, you know, about that long and like a 3/4 inch inside diameter. So I made basically permanent versions of it. I made the cable around those. So I got common mode current chokes at my patch panel here in the shack and out at the antenna that I made using this mechanism. Okay, I did test an ugly balun. I did not measure this or calculate what it was supposed to be. There are all kinds of online calculators to figure out how to design an ugly balun. I didn't use any. I would have had to cut more coax and put more connectors on, and I was kind of running out of time. So I just used a PVC form that I had laying around. It didn't measure great. You know, not nearly as well as compared to the others. I bet you if you calculated this out and actually built one that was the way it's supposed to be built, it would probably work better. But I ended up removing this slide from the presentation because I didn't think I was giving a fair shot to this particular design. Yeah, and so using the same coax and the difference between the ugly balun on a clean coil form versus the Gordian knot, where you use the same amount of coax and the same number of turns and just kind of wrap it around itself, this is the difference. So if you're just going to make a coil out of coax, definitely do it on a coil form, like a piece of PVC or something. Do not do it like a Gordian knot, because you'll get this ugly resonance and it will end up being worse overall. That's it. Q&A. Again, my name is Mark Smith, N6MTS, Smitty Halibut on all the socials. And then here is kind of the TLDR results and links to the actual scientific references. I'll leave that up, but I'll take questions. Any other questions?
I have one.
Yes.
Yeah. What about just clamping multiple ferrites onto the cable?
So yes, that works. The problem with that is that it is a very inefficient use of ferrite. So remember when I said earlier that the inductance of a coil on a ferrite goes up with the square of the number of turns of that coil. So if I have a toroid and I can wrap my coax around that toroid 4 times, that will be 16 times the amount of inductance versus just running the cable through the ferrite once, right? When you are sliding ferrites over that coax, that's basically a 1-turn toroidal balun. And if you slide a bunch of them on there, it's a bunch of 1-turn toroidal baluns. And they add linearly. If you've got 4 of those ferrite beads that you slide over, that's going to be 4 times the inductance of just one of those beads. Whereas if you instead take that coax and wrap it through one of those beads 4 times, that will be 16 times the inductance of one of those beads. And so, yes, you can do that, but it's an inefficient use of the ferrous material.
Okay, thank you.
Yeah. Any other questions?
I got a question. Can you hear me okay?
Yes, I can.
Okay. First of all, I started taking some notes, and I said, okay, 13 turns on whatever. And I've got, my target is the fact that I've got a 40, 20, 10 will have fan dipole fed with a single coax RG8X. And so then you said, well, okay, if I take an FT240-43 and wind a bunch of RG8X around there, but you can't but don't do it more than 3 turns, I'm back to square one.
Okay, so hold on for a second.
Mixed up.
Yeah. So there are 2 different designs here. If you've got a toroid, that you're doing FT, if you're going to be using 8X, I would recommend an FT 240. You want the larger toroid. So an FT 240-43, or a 31 if that's all you've got, but whichever. And wrap as many turns around that as you can. You'll want to put this as close to the feed point of the antenna as you can get it, and wrap as many turns around that as you can. If you're putting connectors on that coax yourself, feed it through the toroid before you put the connector on it. You'll be able to get more turns on there. As many turns as you can, and that will be good. If you've gotten up to 13, that's going to be plenty. If you can fit more on there, great, but don't go overboard. If you can only fit 10 on there, then only do 10. Do whatever you can.
Okay, got it.
Where I said only do 3 turns is if you're doing it with this type of loop. You don't want to do more than 3 turns over here, because that's where you start getting a lot of mutual inductance, or mutual capacitance, excuse me, where you're doing the clamp-ons.
Okay, thank you.
Yep.
I have a question, if I may.
Yes, please.
Hello all. I'm KR7AUH, Elizabeth. I have just put an antenna and finally got it under the sidewalk, and there's not extra coax to make these turns. It's just about the right length. Could I make either of these that I see on the screen? As I see them, it would add 2 more connectors.
Yep.
And do that.
Yes, absolutely.
Okay.
I think the fear of having a lot of connectors in a coax line is overrated, or overblown, I should say. Don't go overboard with the number of connectors, but if you've got a good reason to add a connector to a cable, do it. It'll be fine. The connectors, especially, so PL259 connectors are not impedance matched. So if you are going to choose connectors to put in a line, go with N connectors. N connectors are impedance matched all the way through, and they tend to be watertight. So they are overall a better connector than a PL259. So if you're going to take a cable, cut it, put connectors on either side of the cable, build a thing to put in that spot in the cable and put connectors on it and connectorize everything and put it together, then I would use N connectors. And if you're using N connectors, you're totally fine. N connectors will be almost entirely transparent at HF. N connectors are good up into the gigahertz range. So at HF, it's not even going to notice it. PL259 connectors still do it. But if you get to choose, go ahead and go with the N connectors and you'll be fine.
Something to aspire to. Thank you.
Yeah, you're very welcome.
I have a question.
Mm-hmm.
Hi, this is Barry, K7BWH, and I've been thinking about getting a VNA or one of the nano VNA for a while. What's your favorite one out of the scads and scads of them that are available?
The one with the largest screen. I've not done a side-by-side comparison. I think they're all basically the same technology. The one that I have is not an easy reach, but it's one of the larger 4-inch screens. I think I got one in a metal case because I fully expect to drop it. But from a technology perspective and a software perspective, I think they're roughly all equivalent.
Okay, I understand. It's basically open source hardware, and there have been a whole bunch of Chinese devices out there. Okay.
Yeah. I don't know that any one performs any better than the others, so I just went with strictly physical concerns. Big screen, metal case.
Okay,
Good enough.
Thank you.
Yeah. Anything else?
Brian is holding up something. What's that?
Oops.
Thank you.
I have a question.
Yes.
Can you hear me?
Yes. Go ahead.
I was just curious about what effect changing the diameter on the ferrite has on your inductance. In other words, the one that's on the left side here with the smaller cable, if you had double the size of the toroid, would that cut down on the amount of inductance?
No, if anything, it'll increase it a little bit. So it has more to do with the number of turns than it does the amount of ferrite in the coil. What that's going to do is that's going to give you better power handling capability, actually. So in all of these cases, if you want to be able to handle more power, then double up your toroids or your ferrites, add more ferrite to the material or to the physical construction. And interesting to note, it's not the power, it's not the differential mode power that runs, that matters to the inductor. Because remember, your differential mode power, the power that's actually being sent to the antenna, doesn't matter. There's no magnetic field. It is not seen by the inductor or by the ferrite material, right? What matters is how much is being reflected. So you could be sending a kilowatt to your antenna, but if it is incredibly well matched, and let's say only sending 1 watt of reverse power, that 1 watt is what the choke is going to see. Versus if you've got a 100-watt antenna or transmitter and it's sending back 50 watts, right? You're sending much less power, but much more of it is being reflected. It's the reflected power that's being seen by the common mode chokes, not the transmitted power.
Yeah.
So when people say, oh yeah, this common mode choke is good up to 100 watts or up to 15 kilowatt, 1500 watts or whatever it is, without telling you at what what kind of load that's being measured against, that's being a little disingenuous. Just,
Okay.
because that's not how it's measured. That's not the amount of power that matters.
Got it. Thank you.
Another trick about stacking toroids. You can literally just stack multiple toroids on top of each other and wrap the cable around the entire stack. If you're going to do that and you want to have a wideband antenna, stick a 43 mix and a 31 mix in there. And you'll kind of get this like wider curve, slightly wider curve. You'll get the benefits of both of those.
Okay.
Tom, I was just going to mention the first effect of using larger diameter is it weighs more and costs more.
True.
So is the reflective power that is on the outside of the shield that hits your choke, is it dissipated in heat?
I don't think it's so some of it will be, because it's going to form a magnetic field in that ferrous material, and that ferrous material will have to dissipate it. But I think what happens is that it ends up being a high impedance to that current, and so most of the voltage will develop across it, but that ends up kind of forcing that back into the antenna. And so I think it actually will force your antenna to radiate some of that power.
So more turns through the 240 will actually create a higher impedance device.
Yeah.
Okay.
Yes. Any
ballpark figure on like how much impedance you get per turn, like through a 240?
That's a kind of thing that you can get on a calculator. Toroids.info.
Right.
And look up the FT240-43. Tell it how many turns you have, and it'll give you the inductance.
Yeah, because I've been using these 31s here, and they seem to work pretty good with about 10 turns or so.
Yeah.
Yeah.
Yeah, that'll be great.
Yeah, that'll work, because I got to cut the end off of the RG8X anyway to connect up to the center point. So I'll just wind it around. I just looked up Amazon. They got FT243s.
How much are they?
They're $10.37, I think.
Palomar Engineering has them about the same price.
Yeah.
I mean, the guys on the podcast, like they literally buy them 50 at a time. Like they just buy them in bulk and keep them around the shack. I've got an entire plastic bin in that pile over there that's full of ferrites. And like, it's amazing how much quieter you can make a station by finding your noise sources and choking them off. I recently found out that some LED lights in our living room that I installed, it's a system that I designed and installed, but it's using an off-the-shelf DC power supply. And every time those lights are on, I get the 60 kilohertz, spikes all across the HF spectrum. So I need to get a moment to pull out the couch, get to that power supply, and wrap the leads going in and out around some toroids and see if that improves the noise.
Wait till you put in your solar panel inverter.
I've already got one of those, and it's actually really quiet.
What model?
Sunny Boy. Their SMA now, I think, is the brand.
Yeah. Oh yeah. I have a Solar Edge, and I get tremendous amount of noise between 3 up to about 6 megahertz. And of course, it's entirely dependent upon what the output of the inverter is. So the inverter, if I'm only putting out about 1,000 or so watts, don't hear much. But once it hits about 2,500 watts, you can just see it climb. Mostly just a problem for me on 75 meters,
Yeah.
but the rest of it. But
yeah, I don't notice any obvious change. I've got cutoffs before and after the inverter, so on the high voltage DC side and the AC side,
right.
And I go out and cut those off, and I don't notice any obvious change in my noise floor.
Yeah.
Mark, I have a quick question for you.
Yes.
Not a electronics person by any stretch. I understand a great deal of what you said, but if you had one of these tuners that's placed right at the base of the antenna that you can control through the coax, is that just as good?
So tuner is a misnomer. They are an adjustable matching network. They don't actually tune your antenna. They just match the impedance of whatever complex your antenna is to the 50 ohm characteristic impedance of your coax. No, I don't think that would affect this. I don't think that would fix this problem. I think you still need to have a current choke.
Would that be at the transmitter and also behind this tuner?
Yeah, why wouldn't it be if we recommend a 1-to-1 balun at a dipole, which is as resonant
as you can get,
as we're gonna get in the real world.
Yeah.
But it still balances that out, right?
I'm going to claim ignorance on this one. I don't know. Short answer is these are cheap and easy to make. Put it in. It doesn't hurt. One thing I didn't show in these slides is through all of these baluns, I measured the through of the coax, and it was always 0 or damn near 0. Right. So putting this balun has no effect on the desired differential mode that you're trying to send through the coax. Right. So it's completely transparent to the things that you want it to be transparent to. I should have put a slide in there showing that. So it doesn't hurt. It never hurts to add one of these common mode current chokes. So the safe thing to do, if you've got a non-resonant antenna, and then you've got a remote tuner right at the base of that antenna, right at the feed point of that antenna. I don't know whether that will address the imbalance problem, but it certainly won't hurt to put a common mode current choke right at the feed line side of that tuner, of that matching network. And that will fix any imbalance on the antenna side. And then you still want to have a common mode current choke at your receiver to stop the feed line from being an antenna. So remember, we got 2 different places to put the chokes, and they're solving different problems, right? So it's not can I do one or the other? Like, you can, but you're only going to solve one problem or the other.
I had very good results with the remote tuner by having a balun both at the antenna connection and on the coax. And I think you're right. I think you should do both.
Yeah,
Don't
well,
mix up VSWR with unbalance.
Yeah, that's true. Those are separate things.
anybody else?
Yeah, one other question. I picked up some toroids from, you know, junk box type things and looked at them. They were all basically little ones and stuff like that, and have no idea where they came from or anything else. So
I got a box of those over here.
yeah, is there any way? I mean, outside of the size and, you know, wind and everything else, how do you tell what the heck you got? Because there's no markings on the things.
There are no
I mean,
markings on them.
some are green, some are black, some are red. Most are red.
Okay, those are probably iron toroids, not ferrite toroids. So I think the painted ones are the T number dash mix, not FT number dash mix. And they're different chemistries in the ceramic that makes up the toroid. I can't go into the details on the distinctions between them. The FT tends to be much higher in inductance per turn than the Ts do, but I think the Ts can handle a lot more power or something along those lines. I don't remember exactly what the trade-offs, but the ones that I found that are painted tend to be the Ts, not the FTs. So the way you figure out what a mix is, there are some very scientific and very complex ways that you can use a VNA to measure very specific, the permeability is what you're trying to measure. And there are ways of measuring that with a VNA. I can't tell you what they are. Go Google it. There are lots of different things. They tend to be somewhat complex, and they kind of, the articles are written assuming you're already an RF engineer, which I am not. The way that I've thought to do it, if you kind of have a rough idea of like it's this size, and so I think it's either this mix or that mix or something, wrap a number of turns around it, measure the inductance, get a good inductance meter, measure the inductance of n number of turns around that toroid, measure the inductance, and then go to toroids.info or look it up in a reference and see if you can find which mix with that number of turns produces that inductance. You're not measuring the properties of the material directly, but I think you can get a pretty good idea based on that.
Okay,
I have not actually done this myself.
Anything or built anything with toroids, so I'm looking at it and said, well, they look like they skip across a pond pretty well. You know, but outside of that, if I couldn't find out what it is, maybe that's the best alternative. I have no laboratory equipment to do what you're requesting. So
nano VNA is only $50.
well, that's true.
Put it up for
Right.
a club vote
Inductance
there.
meters you can get for less than 100 for a good one. Decent
The way
one.
I measure inductance is I have what I call a standard oscillator, and it's an oscillator circuit, and I stick the inductor on it and I measure the frequency, and then I calculate what the inductance is. And it's very simple to make that out of just one transistor.
Yeah.
And a couple of capacitors. Yeah.
A quick question.
Yeah.
Directed at Walt, actually. Walt, could you just expound on your statement very quickly? You said, don't mix up the VSWR with the imbalance. Is that correct?
Yes. Yes, there are different issues, and the toroid that we're talking about here is going to correct for unbalance, but it's not going to correct the basic VSWR of the antenna.
Okay. Good stuff.
And
Thank
I think that the counterpoint to that is that the remote antenna tuner at the base of your antenna will fix the VSWR, but not the imbalance.
That's correct.
Yeah.
Okay. Thank you.
Another question.
Yep.
Quick question. What about VSWRs for if you have a VSWR, meter inside your radio? Will that same thing?
Well,
For-
if you're measuring the SWR at your radio, you're measuring the SWR of the entire system, including your feed line.
okay,
That's not
and
going
I
to
know-
tell you what the SWR of your antenna is.
Yeah, I mean, yeah, I know that, but the radio corrects for that at that point and runs it down to the lowest SWR that it can do.
Oh, so you're talking about an antenna tuner
Yeah.
in the radio. Okay. But again, it's measuring, it's matching what the coax in the back of your radio is to 50 ohms of the radio. And, you know, the coax that's supposed to be 50 ohms is now whatever impedance it is coming down from your non 50 ohm antenna and stuff. So antenna tuners in the radio are meant to save your radio. They are not meant to match your antenna.
Okay. I got a big KT34XA up there. It seems to work pretty well.
Yeah.
Was there another question? I thought there was.
Yeah. So what if I
Barry.
have a lightning arrestor? I don't have one. I intend to put one just on the outside wall. Will it make a difference where I put in that line the choke coming into my radio? Whether it's outside the lightning arrestor or inside or at my radio or what?
So there are two conditions here to consider. One is the normal everyday operation. No, it won't make a damn bit of difference. The second one is the lightning case, and your ballon's going to be toast. So it doesn't matter which side of the arrestor it's on. Your
Okay.
ballon's just going to explode along with your antenna.
Then
I mean,
possibly
the
radio.
ballon's the cheap part there, right? Like the lightning arrestor is there to save the antenna, or no, sorry, not the antenna, save the radio and the house, the
house,
structure that the
yeah,
radio
yeah.
is in, right?
Mhm.
The
Well,
ballon
it also
is
helps
a
with
cheap.
static flashover.
Say again?
I'd say it also helps with static flashover because it'll fire, if it gets above a certain voltage across
Yeah.
that gap, and go to ground. Many times you'll never know it. And it's so quick. I mean, it's no damage to the radio
Yeah.
and everything else, and it doesn't destroy itself. It's just there.
Okay.
And it wasn't a lightning strike. It was, just
Yeah. Just wind.
right.
But the common mode current choke won't make a damn bit of difference to any of that.
All right. Thank you.
Mhm.
Awesome presentation. Thank you, Mark.
Thank you.
Yeah, thank you so much, Mark. Anybody else
Thank you.
have questions for Mark? I think you solved at least two of my problems here tonight. One is my homebrew 10-meter 2-element Yagi. I thought it'd be clever and just wrap 6 turns of coil around itself, the coax. So clearly that's what's going on there. And what's the other one? Oh, I bought some big fatty toroids to put on my generator extension cord on either end of the cord. I'm really looking forward to testing that out. But
Yep.
that's,
Yeah, generators, especially if you've got
I have
like the
here
old
somewhere.
analog generators are usually pretty RF quiet, except for the spark plugs are not necessarily. But like if it's just an alternator that's where the frequency of the AC is dependent on the RPM of the engine, there's no switching or anything in there. And so those tend to be reasonably RF quiet. The modern switching mode generators are the ones that you have to worry about. Having said that, Honda makes a really good inverter. It's very quiet.
There you go, Ed.
Yeah, I don't want it'd be my third generator. I might buy one of them, but I think this is going to help me. It's bog you down. It's actually going to be fun to test out, but it's very specific to the lower bands. I mean, 80 and 160 meters.
Yeah.
And I think I've got here. In fact, here's one of the Toroids with my camera. It's like a 3-inch inner diameter. I mean, this thing's
Here.
an expensive behemoth, but
Yeah.
looking forward to testing that out.
Show
Anyway.
it again. Sorry, I was still on
Oh,
speaker.
yeah, yeah.
Show it again.
Where's my camera?
Oh, geez. The
Yeah.
FT72-3, 727. That's a big toroid.
I have one small comment.
Yes.
Go ahead.
Where capacitance might be a little bit of a problem, just adding a little bit of extra spacing where possible on the wraps will reduce that.
Yes.